Okay, so this is problem 2.34 out of Griffiths, and wants us to find the energy stored in a uniformly charged solid sphere of radius r and charge q, and it wants us to do it in 3 different ways. I'm only going to do A and B. C doesn't really seem practical in a lot of ways to me because it requires your E field and your B field, or your, not your V field, your potential and your E field. So, I mean, if you have one of those, you can solve it the other ways. So, I'm only going to do A and B. Now, the equation we're going to use for A is our energy is going to be 1/2 integral of rho times your potential times d tau. So, if you have the potential, you can find this. And it mentions in problem 2.21, which I believe I did a video on that. Yes, I did 2.21. You can watch the video here on my channel, but I'm just going to use the results that we have there, which is the potential is equal to Q over 4 pi epsilon naught times 1 over 2r times 3 minus little r squared over big R squared. Now, rho is your charge density. So it's the charge Q per volume, which is 4/3 pi r cubed, which is 3Q over 4 pi r cubed. So now with all that, we can plug this into our equation. So it's 1/2. This is going to be a triple integral. It's a volume integral from 0 to 2 pi, 0 to pi, 0 to r. Obviously, this is a sphere, so we're going to use spherical coordinates. And what do we have? Well, our potential, or I'm sorry, our rho, this guy, 3Q over 4 pi r cubed, times your potential, which I'm just going to simplify that by multiplying the 4 and the 2 together. That's 8 pi epsilon naught r times 3 minus little r squared over big R squared, and then d tau, your volume element, which is r squared sine theta dr d theta d phi. So we have to solve this integral here, and then we can find our work. So the d theta d phi term will get you 4 pi. So if we evaluate the first two integral, or the first two integrals, you get that. And then it turns into an integral of just dr, which is 3q squared over 4 times 8 is 32 pi squared r to the 4th epsilon times 3 r squared minus r to the 4th over r squared dr. Okay, so let's just simplify this a little bit. This can be a 2, which then can go to 1 if this becomes a 16. This pi will cancel with that pi. And perfect. So then you get 3 over q squared, so I'm factoring outside, that's all constant, 16 pi r to the 4th epsilon naught, and then I'm just going to break this up into 2 integrals. The integral from 0 to r of 3r squared dr minus 1 over r squared, the integral from 0 to r to the 4th dr. So just using linearity there to make this integral a little easier to do. Okay, so we will get our energy is 3q squared 16 pi r to the 4th epsilon naught. So when we evaluate that first integral, it'll just be r cubed, right? Because you add 1, this is just a power rule. minus 1 over r squared times 1/5 r fifth. Which this will drop here to get you a 3. So it's really 1 minus 1/5. Or you could think as r cubed minus 1/5 r cubed. So then this is equal to 3 q squared over 16 pi r to the 4th epsilon. So that's going to be 4/5 r to the 3rd. And we can simplify this a little bit. Let's see. So this goes here, which goes to 4. So this is 3 times q squared over 4 times 5 is 20 pi epsilon naught times r. So that's one way that we can get the energy stored. The other way we can do it is to use equation 2.25, which just says work, or the energy, is equal to epsilon naught over 2, the integral of the magnitude of your E field squared d tau. So if you have the potential, you can do part A to find that. If you have the E field, you can do part B to find the energy. And part C kind of uses a combination of both. So I'm not going to worry about that one. Now again, this was given in that same problem. So E field N is 1 over 4 pi epsilon naught times QR r cubed r hat. And E out, again, if you're not okay with this, you can rewatch the video and we actually get the E field and the potential. And these were our results. So with that in mind, we can use this to, this is actually probably a little bit faster. We have epsilon naught over 2, again a triple integral from 0 to 2 pi, 0 to pi, 0 to r. So because we're integrating from 0 to r, this is your inside. So we take our E field on the inside, and we square it. And I'm just not going to worry about the direction because, again, it's just the magnitude. And then we have the volume element. So r squared sine theta dr d theta d phi. Plus, we do have to do another triple integral here, and that's because we have a different E field when you're outside. So from r to infinity. So that's your E field outside. So 1 over 4 pi epsilon naught times q over r squared squared. That's your outside E field squared, the magnitude of it. And then times r squared sine theta dr d theta d phi. The volume element and spherical coordinate. So it's maybe a little bit messy here. Close that off in parentheses. But it cleans up pretty nicely. So we have epsilon naught over 2. Both the terms, both the triple integrals will give you a factor of 4 pi when we do our theta and phi. Both terms have a 1 over 16 pi squared epsilon naught squared, just from the constant. And both will have a q squared. So then we just have 1 over r to the 6 if we square this guy. The integral from 0 to r. So we have r squared times r squared, so that's r to the 4th dr. Plus the integral from r to infinity. So that's 1 over r to the 4th times r squared. So that's 1 over r squared, or r to the negative 2 dr, just to make the power rule a little easier. Okay, so this epsilon naught will cancel with 1 here. This pi will cancel with 1 here. That makes this a 2. And that goes away if we make this an 8. Okay, so we're going to get just q squared over 8, just pi, just epsilon, times, so what do we have? We have 1 over r to the 6 times 1/5 r to the 5th, if we do the power rule. And then we're going to get minus 1 over infinity minus 1 over r, if we evaluate that one. Now this is obviously 0, we don't need to worry about that. This will drop with all but 1 here. So the energy we get is q squared over 8 pi epsilon naught, 1 over 5r, minus the negative, plus 1 over r. So now that we have that, you could just get your common denominators. You'll get q squared over 8 pi epsilon naught times 6/5, 6 over 5r. Let's see, this will become a 4, this will become a 3. So you get 3q squared over 4 times 5 is 20 pi epsilon naught r. And if we look up, that's exactly what we got here. So we're able to get the same answer doing 2 different ways. And one uses E field, one uses potential. So I think that was worth going over. Hopefully that helped out.